Hello, my name is James Han, and this is my Lab 2 video report for Physics 2211 on projectile motion. In this lab, I observed the motion of a projectile, analyzed it using tracker software, and built two different computational models in GlowScript to compare the real motion to theoretical predictions. This experiment focuses on understanding how forces, especially air resistance, affect the path of a projectile. The purpose of this lab was to build computational models using Newton's second law and compare them to experimental data from a real projectile. Specifically, I wanted to see how adding drag changes the predicted trajectory compared to a gravity-only model. I recorded the motion of a paper ball, analyzed its trajectory, then modeled its motion step by step to match what I observed. The foundation of this lab is Newton's second law, which states that the net force equals the rate of change of momentum. For the model, I used velocity and position update formulas to numerically integrate the motion over small time steps. Gravity acts downward with a force of F equals mg. The drag force is modeled as force of drag equals negative bv squared, which points opposite the velocity direction. This is important because the drag force depends on the speed squared, so its effect becomes more noticeable the faster the object moves. Here's a quick preview of my result. The computational model that included both gravity and drag produced a trajectory that was very similar to the tracker data. In contrast, the gravity-only model predicted a longer flight range and a slightly higher arc. This suggests that even for something as light as a paper ball, air resistance significantly affects the motion. The system in this lab is a paper ball itself. The surroundings include the air and the earth. The main forces acting on the ball are gravity acting downward and air drag acting opposite to its velocity. Identifying system and surroundings is key because it tells us which forces should be included in the model. For the experiment, I recorded a throne from the side using a fixed camera to minimize parallax. I placed a ruler on the ground to calibrate the scale in tracker and set the origin directly below the launch point. Using tracker, I marked the ball's position in each frame to get time, x, and y data points. The graph shows a smooth, curved path, exactly what we expect from a projectile under gravity and drag. Next, I built two computational models in GlowScript. The first model included gravity updating velocity position step by step using like kinematics equation derived from Newton's second law. The second model added a drag force term that depends on the square of the velocity. By adjusting the drag coefficient, I was able to get the simulated trajectory to closely match the experimental data. Both models used a small time step of 0.001 seconds to minimize numerical error. Here's the key comparison between the tracker data and my gravity-only model. The blue points are the experimental data, and the red line is the gravity-only prediction. You can see that the model overshoots the experimental range and doesn't quite match the height perfectly. This makes sense because without drag, the ball keeps more of its horizontal velocity and stays in the air longer. When I included a drag, the predicted curve matched the blue data points much more closely, both in peak height and landing position. There are a few possible errors in this lab. Small clicking errors in tracker can shift the measured positions. The camera might not have been perfectly perpendicular, introducing distortion. Air currents in the room can slightly change the flight path of such a light object. And finally, estimating the drag coefficient is never exact. It can vary with the ball shape and orientations. These errors together explain the small difference between the model and the experimental data. Let's look at the what-if questions. First, terminal velocity. The gravity-only model doesn't predict the terminal velocity because there's no opposing force. But the model with drag does. Terminal velocity happens when the drag force equals the weight. For my object, the predicted terminal velocity was around 6.3 meters per second. To actually measure it, I needed to drop the ball from a higher place so it has time to reach that speed. Second, if I threw the ball straight up with the same initial speed, the total time in the air would be longer. This is because all the velocity is in the vertical direction and drag acts directly against it, slowing down more on my way up and down. In conclusion, this lab showed the importance of including drag and projectile motion models. The gravity-only model gave a clean parabolic shape, but the real motion was noticeably affected by air resistance. By combining experimental data from tracker and computation models from GlowScript, I was able to see how theoretical prediction compared to real-world behavior. This approach of modeling, testing, and refining is a core part of how physicists and